So we have been discussing about the photochemistry of carbonyl compounds, and we have already looked into several examples of Noyce type 1 reaction and then Noyce type 2 reactions. Now today we would like to see few examples based on Noyce type 2 reaction, which is the gamma hydrogen abstraction by the excited carbonyl, and this has been exploited for the synthesis of synthetically important reactions. So uh, the say for example, if benzophenone is a very good sensitizer, and then examples of type hydrogen abstraction, uh, examples of synthetic application, examples of synthetic application of photochemical of photochemical hydrogen abstraction. So in this one, we have a benzophenone. This, in the presence of light, can go to an excited state, excited carbonyl, and this excited carbonyl yeah, the reacts with uh, benz hydrol. So say for example, can abstract an hydrogen atom from benz hydrol. So H, OH, this is your pH, this is pH. The excited, this is benz hydrol. So excited carbonyl abstract an hydrogen atom from this, and then we get OH, pH. So this radical plus, and from this one OH, and then they get a pH. So we get a pair of these radical species called ketyl radical pair. This is ketyl this ketyl radical pair can undergo radical coupling to give a product like this, pH, OH, and this is called benz-pinacol. So it is a simple reaction where it is possible to synthesize benz 1,2-diol, that is called benz-pinacol, just by the excitation, photo excitation of benzophenone, abstraction of a hydrogen atom from benz hydrol to give the corresponding radically species, and then which will combine to give first to give a ketyl radical pair, and then this is a first example. Second example is the photo reduction of benzophenone to photo reduction of benzophenone this one, this is benzophenone. So photo reduction of benzophenone to benz hydrol, hydrol in by alkaline isopropoxide, by alkaline isopropanol. The second example of the hydrogen abstraction by the excited carbonyl to give synthetically important compound. And let us see, as usual, we have a benzophenone. This, in the presence of light, goes to an excited carbonyl. This excited carbonyl can abstract an hydrogen atom from isopropanol. This is isopropanol. Hydrogen abstraction by excited carbonyl to give isopropanol, to give, as usual, the ketyl radical pair pH plus from this one. We have already seen first example. Second example is the photoreduction of benzophenone to benzhydrol, and then so if we have as usual, if we have a benzophenone in the presence of light, a second example of a synthetically important hydrogen reaction which involves the hydrogen abstraction by excited carbonyl to give a ketyl, the ketyl radical pair, which in turn undergo coupling to give important product. So, as usual, this in the presence of light goes to an excited carbonyl, pH. This excited carbonyl abstract an hydrogen atom from isopropanol to give a ketyl OH, pH plus OH. This is to give this one ketyl radical pair, ketyl so ketyl radical pair, and then this ketyl radical pair in under alkaline condition, OH minus. Of course, there are several steps involved in which this lead to anion, corresponding anion of this this species plus this will abstract in hydrogen atom, followed by and then this is leading to acetone, and this can abstract an hydrogen H plus to give OH. So the photoreduction of benzophenone, so ultimately this one is going to photoreduction, is nothing photoreduction in the presence of light, photoreduction, the presence of isopropanol under alkaline condition where we have a involvement of, so you can see that the benzhydrol, so it's going to give benzhydrol as the product. So photoreduction has been reported under similar condition to give this. Now let us see a few more example, and this is third example of the synthetically important hydrogen abstraction by the excited carbonyl, benzophenone isopropone containing malic acid. The reaction of excited reaction of irradiation of benzophenone irradiation of benzophenone in isopropanol containing malic acid. So you can see that the malic acid add to the excited the ketyl radical to give a very interesting product. So you can see here to give cyclic product or cyclic product or which is lactone. So we can see in this reaction benzophenone under photolysis in isopropanol containing malic acid gives rise to cyclized product that is lactone. So we start with, as usual, we have a benzophenone pH benzophenone under photolytic condition goes to excited carbonyl. Excited carbonyl in the presence of as usual, as we have seen in the previous case, excited carbonyl abstract a hydrogen atom from isopropanol to give a pair of ketyl radical pH plus ketyl radical pair this ketyl radical pair this radical adds to malic acid. So this adds to malic acid to one of the olefinic carbon to give a product like this. So we have this one a radical. So we'll just write a carbonyl here, OH and radical. This is these parts COOH. A radical is coming here, and then we have this is isopropanol. We have COOH, this one, and this part this is the isopropyl part. So we get this. So this isopropyl part link this carbon is linked with this, and then the radical. Now this radical in the presence of the radical which is generated can abstract an hydrogen atom, and then this becomes benzophenone and to give a can abstract an hydrogen atom. This is going back to benzophenone is generated again, and then we have a COOH. Right, and this is cyclizes by losing water to give COOH, and this is a carbonyl. So you can see a very interesting cyclized product, the lactone, which is formed by excited carbon in the presence of isopropanol. The reaction is extremely simple. Benzophenone goes on absorption, it goes to excited carbon, abstract a hydrogen atom to give a ketyl radical, which the isopropyl radical adds to benzoic acid, followed by abstraction of hydrogen atom back from benzophenone radical to give this and then this cyclizes. So you can see very interesting products have been obtained from the hydrogen abstraction program. Only the question is we have to select the proper I mean species or so. Another another example where the extension extended for alkyne. So this reaction can have also been extended. These reactions have been extended for alkylating protein, for alkylating protein. So let us see. So as usual, we have a benzophenone, acetophenone. So acetone, in the presence of light, goes to an excited acetone, and then this is acetone, excited acetone, and then so this can add to the glycine residue, NH, CH, CONH. This is the glycine. So the excited acetone abstract in a hydrogen atom from the glycine residue to generate ketyl radical plus NH, CH, CONH. So you can see, as usual, we have a ketyl radical pair. This ketyl radical pair can add to, so we are talking about alkylation of protein. So this can add to an alkene. The reaction of this, so R, CH, double bond CH2 is a substituted alkene. This can add to this carbon, because going to give a secondary more stable carbon, because other attack is going to give a primary carbon. So this will lead to NH, CH, CH2, CHR is a radical here, CONH. So this radical once again can abstract a hydrogen atom from the this other isopropyl ketyl radical to generate the modified, and this will of course generate back to acetone, NH, CH, CH, CH2, CH2R is going to abstract an hydrogen atom, and this goes back CONH. So you can see the modified protein or alkylated protein. So this how we are able to synthesize, we are able to use hydrogen abstraction for synthesis of a large number of synthetically useful compound. Let us see further synthetic application using unit types. So few more examples of examples of synthetic application of more examples of synthetic application of Norris type 2 reaction. So in this one, we have to just select the proper starting material where the carbonyl and gamma hydrogen is set for carbonyl set for gamma hydrogen abstraction by the excited carbonyl. So this is an asteroidal system. We have already seen few examples of uh, the type 2 reactions where the this is a carbonyl, this is a pH here, this is alpha, beta, this is a gamma hydrogen, and there is an H here. So this in the presence of light, the carbonyl goes to excited state, is also set for gamma hydrogen gamma hydrogen abstraction, abstraction by excited carbonyl. So we end up with a product. We get a 1,4 diradical. This is bridge-head methyl groups. There are 2 methyl groups at this carbon. This is 1 carbon. This is another carbon. This is going to abstract. This is a 1,4 diradical species. Diradical 1,4 diradical. Now there is a possibility of the combination of these going to give you a 4-membered ring, which looks slightly unstable, but and so therefore this undergoes it is nicely may cleave to give an exocyclic double bond to this asteroidal system. This is really interesting because the generation of a double bond to the asteroidal system to exocyclic position is really a good synthetic route, and hence we have a OH, pH. This is a enol form get tautomerized to keto form. So you can see this starting material is nicely set for the gamma hydrogen abstraction by excited carbonyl to give an exocyclic double bond. So this is again an important aspect of this reaction. Let us see for a few more examples. This is another example where we have again so selection of the suitable starting material is important. We have a double bond here. We have an ester. The carbonyl is a part of an ester, O C2H5. This is a hydrogen here. So this is alpha, this is beta, this is alpha, beta, and this is gamma. So this under photolytic condition, the excited carbonyl goes in excited state and nicely set for gamma hydrogen abstraction to generate 1,4 diradical. Gamma hydrogen abstraction by excited carbonyl to generate 1,4 diradical to give a species like this. You have a radical here, we have the double bond here, you have an of course OH after abstraction of the hydrogen atom is OET. Now this is again if we can combine this is a diradical. It is going to be a highly unstable system because it's connected to a 6-member ring, 4-membered with a double bond. So it is nicely set for because both the radicals are in conjugation with the double bond, so it can generate another species like this. Now this is the enol form. This is enol, and then this will tautomerize to keto form. So we can see this is a and one extra carbon. One, two, right. So this is really interesting to see that we end up with a this starting material uh, gives this keto form, and then this on excited carbonyl. We can also see another example here. This also involves similar. There is a methyl group, is a benzoyl group. This is a methyl group. We can write H here. This alpha, beta, gamma. So this under photolytic condition, the excited carbonyl can abstract a hydrogen atom. CH2 radical, OH, pH, diradical species. Diradical species, and this diradical species again it is in conjugation with the as in the previous case, the radicals are in conjugation with the double bond, so we can get a species like this. And this it has been shown that these two double bonds acts as a diene, acts as a diene, acts as diene, and may react with the dienophile, like dimethylacetylene dicarboxylate, say COOR. COOR is a very good dienophile, dimethylacetylene dicarboxylate. So this is going to give a this. So we can see that this is nicely set for a the benzene ring. Now it is connected with a cyclic. Is a really a great very interesting R, COOR, and then this is PHOH, and this of course get aromatide. So here we can see a very good example of a excitation of the carbonyls. I mean the excitation of carbonyl reacting with the benzene ring. You can see a few more example here. So there is another example where we have seen that this is also an asteroidal system, and it can nicely go for an intramolecular intramolecular. So it is a Stoichel system. We can write these one double bond and another double bond on a one. So a Stoichel system, and then we have the ester O, C double bond O. This is CH2 CH2 twice, and then we have a. So people have just tried to people have tried. Oh, sorry. People have tried a different. This is a benzoyl group, C double bond O. So this is a hydrogen from the second. This is this excited carbonyl can abstract in the presence of light. Excited carbonyl can abstract a hydrogen atom. So of course, is a carbon chain is quite long enough and have is can may so long enough to abstract a hydrogen atom from this position to give a radical species, a 114 diradical. So you can see here we can write as usual the Stoichel system. Of course, we have a cell group here, this is R here, and so on and so forth. And then we can think of a diradical. So as usual, the other part CH2 twice, and then you have a ketyl, this ketyl radical, C radical OH, and then of course this is a part of the Stoichel system. So here this is very interesting example of intramolecular hydrogen abstraction by the excited carbonyl, and if the ester is quite good chain, so that it may abstract the corresponding the hydrogen abstraction by the excited carbonyl to give so this will once again is a methyl group is combine this is 114 114 diradical, because if we can number this 1 2 3 4 5 6 7 8 10 11 12 13 14 1 2 3 4 5 6 7 8 9 10 11 12 14 carbons, 114 diradical. And then this will combine to give a cyclic product 14 give a 14 membered ring. So this will combine to give 14 membered. So we can see by selecting a suitable substrate. This is the part of the Stoichel system. This O, C double bond O, CH2 twice. This is a benzene ring. This is a carbonyl OH. This is a ring. This is a new bond formation, and then we can see that can go to a cyclic system. So you can see a very interesting product could be obtained by similar abstraction by the excited carbonyl and to give this same as the another example of a intramolecular hydrogen abstraction has also been reported by the another example of intramolecular hydrogen abstraction um, by taking a, you can see this is the is a thalide, C double bond O, CH2, CH2 5 times, S, CH2H. You can see under photolytic condition, under H nu, the carbonyl goes to an excited state. This excited carbonyl can abstract a hydrogen atom to generate the corresponding diradical, C double bond O N OH, a diradical CH2 5 times, S is a sulfur here, is a CH2 here, is a diradical, and then this will combine to give a cyclic product. CH2S, you have a CH2 5 times, and see the so this is a really a cyclic product. So by taking a suitable starting material and then the excited carbonyl may also abstract a hydrogen atom intramolecularly to generate a diradical species, and which may combine to give the interesting synthetically important cyclic product, as we have seen in this one as well as, and this one you can see a 40 membered ring, and this is a next one is a 1 2 3 4 5 6 7 8 9 5 6 7 8 9 10 membered ring system. As a new 10 membered ring system is formed by the abstraction of the, so these are few examples of the the abstraction of a hydrogen by excited carbonyl to give a diradical species which can be exploited, may act as a diene system and can act easily to dienophile like dimethyl acetylene dicarboxylate. So this is a R is equal to methyl. This can be dimethyl acetylene dicarboxylate. This CH3, COO CH3, COO CH3, COO CH3, COO CH3.